Hi, this is Katie Miller, and today we are going to be talking about a problem that has to do with this network of pipes. So you can see we have different nodes, 0, 1, 2, 3, and 4, and we have water going through it, and so node 0 is our source node, so that's where the water is going in, and the water is coming out at at node 4, which is our sink node. And some of the values we know is at node 0, we know that the pressure is going to be 200,000 pascals and the height is 30 meters. And for 1, 2, and 3, we are going to say that the height is 0 meters and we don't know their pressures, those are unknown. And for node 4, we know that the pressure is going to be 0 pascals and the height is also going to be 0. This is our diameter of the pipes is 0.1 meters, and the relative roughness of these pipes is 0.001. So since we know that, we are going to start with our code. We're going to import SciPy as NP, and this will help us with certain mathematical functions that we're going to use later, such as logs, absolute value, and sign changes. And we're also going to do from SciPy.optimize import Newton and root. And this stuff is going to help us with a function that we're going to make later on. There's a certain Newton equation kind of thing that will help us with that. And so we are going to put in some values that we know, which is one of them is gravity. That's going to come up in a lot of our equations. We know rho, which is the density of water, and that is going to be 1,000. We know mu, which is the viscosity of water, and that is going to be 0.001. We know the diameter, which is 0.1. There we go. And we know the relative roughness, which is 0.001. And so now that we have that, we are going to go back, and this is an array that we have that we will use later. It has the k value for from one node to another. It's giving us the k value and the length. And if we look down here, this is our Bernoulli's equation. This side here is going to be our change in head, and this side is going to be what we are going to solve for later. And we know all of these values. We have L, we have D, because we have the lengths and we have the diameter. And we can find the velocity using this equation, but we don't know this F, which is our friction factor. And so to find that, we are going to use our Churchill's correlation. And so these are the equations that we have to find that. And if you see, A and B are represented here, and we have all of the numbers that we need for that. So what we are going to do is we are going to start out and make a function finding that. So we're going to do define, and I'm just going to call it F, and we're going to take in the Reynolds number and the relative roughness, and we are going to put in those equations for A and B. So let's see, A is equal to 2.457. We're just going to put this in parentheses, times the log, so NP log of 1 over 7 divided by the Reynolds number to the 0.9 plus 0.27, pretty sure, 0.27 times ED, all of that to the 16th power, I believe. Yep, 16th power. And B is pretty easy. It's just going to be 3750. Is that right? 37530. Oops. 30 divided by the Reynolds number. And we are going to return, that's not how you spell that, return this equation. So we don't need that. So we are going to have 2 times 8 divided by the Reynolds number to the 12th plus, let's see, it's 1 divided by A plus B to the 1.5, and this whole thing is to the 1/12. So shift enter, we get no errors, and we're just going to check this with some random numbers. Let's say, I don't know, 25 and the value we have for ED. If we run that, we get a number, and that's good. So that means that our function works. And so now that we know the fiction factor, we want to solve for the change in head. So we're going to make another function, and we are going to have this equal to the negative of this value. So if we move this to the other side of the equation, we would have a negative of this value. So what we're going to do is we're going to define another function, and we're going to call it d head because it's the change in head, so that represents delta head. And our inputs are Q, L, K, D, and ED. And so we are going to have, we want to find the velocity. So we're going to have V is equal to, and we're going to put an absolute value here just so we don't have a negative number coming up when we run the function. So it's going to be Q over np.pi times d squared divided by 4. And then we need our Reynolds number, which is going to be rho, this rho times V times D divided by mu. And what we want it to return, I can't spell return. Okay, what we want it to return is the opposite sign of this side. So what we're going to do is we're going to say negative np.sign, and so if it is a positive sign, then it's going to give us 1. If it's a negative sign, then it'll give us -1, so it'll switch it. And so we want that to be Q times K plus 4 plus F of REED, because that's what we had, times L divided by D, all of that times V squared divided by 2 divided by G. And so if we run that, no errors, and we can put in some random numbers to check it. Q, let's do 5. L, we have, let's say, 1.5. K, we'll do 2.0. And ED, we're just going to have set as that. So let's run it. Okay. I might just need to put a number here. Nope. D head missing. Oh, I'm sorry. I forgot that this is D, so now we need ED. There we go. That should work. SciPy has no abs. Huh. Not sure why it's giving me that. Do I need to run it again? So now that we have a function that is calculating d head for us, we also want to make a function that is calculating the flow. So we're going to define a function of flow, and it has the same inputs as this. However, the q is going to be replaced with delta head, but we don't want to write d head because that will want to take in the function, and that's not what we want, so we are going to write out delta head. And what we want this to return is the resulting flow rate. And so for now, we're going to leave this, and we're going to make another function, and this is going to help us find the function going to 0. So we want this whole equation to go to 0. So what we have to do is make a function again. I'm going to call it f to 0. And the only thing this is going to take in is q. And what we want it to do is the same thing that d head did, is we want it to calculate the velocity and the Reynolds number. And what we want it to return is delta head plus this right side of that equation that we were talking about. So we want it to give us this equation, and we are going to want it to give us 0, but we're going to see if that is going to work. So we're going to make up some numbers. Let's say delta head is 40. What else do we need? We need L, let's say 0.5, we need K, so let's say 1.5, and we have D and ED up here, so if we do F to 0 of, and we're gonna guess for Q, let's say 10, if we run that, you can see it's giving us this number, and that's not what we want because it should be giving us 0. So that's where this Newton's equation is going to come in, because we are going to make a guess for Q, and it is going to take that guess and reiterate it over and over until it gives us the correct value for the variable. Okay, so since we saw that this is not correct, we have to make our Q guess. And so what we're going to do for that, if we look at our Bernoulli's equation, we have to find how velocity and the flow rate relate, and if we look at this equation, that's how they relate. And so if we can take this equation and solve for the velocity, we can use that velocity and solve for Q. So what we can do, I wrote it down here, this is the equation for V, and we can multiply that by the area of the pipe. So what we're going to do is we're going to write Q guess is equal to np.pi times d squared divided by 4 times the square root of negative delta head divided by, I believe it's k plus 4 times f, which we are going to assume is 0.01 times L divided by D, and all of that is going to be multiplied by 2 and multiplied by G. So if we run that, and we can look at the value for that, and so if we look at that, we want to now use our Newton's equation, and we're going to put in F to 0 and Q guess, and they should be very similar, so it looks like I'm messing up something. Let's see, I think there might be something. Here we go. This should be multiplied, and I copied that from something else, so this should also be multiplied. So if we rerun that, rerun everything basically. Rerun that, rerun this. Okay, it's still wrong. Let's see. QGuess. Did I type this wrong? Negative delta head. Square root 2 times G. Let's see. So this is negative delta head over K plus 4 times F times L over D. K plus 4 times F times L over D times 2G, and all of that is under the square root, right? Yeah. And that's pi times D squared over 4. Okay. I'm gonna remove that. Yeah, that's not gonna change anything. To 0. So is there something wrong with this? Oh, I did not mean to do that. Is that what that was? Here. Oh, there we go. Oh, that's okay. Huh. Okay, I'm going to come back after I figure this out because it might take me a little while. Okay, so I ended up figuring it out. I was missing a parentheses, but now if we look, our QGuess and our Newton's equation are pretty close. And now that we can see that, we can rearrange a little bit, and we are going to end up putting this function inside of our flow function because we never really finished that. So I'm gonna tab over, gonna leave some spaces. And then we also want to put our equation for the QGuess in here. Tab it over, and we can delete that, and we can delete this, and that, and that. And so now that we have this, we want the resulting flow rate to equal the Newton equation that we had before of F to 0 with QGuess. And if we run this, so flow of, let's see, I had 40, L was 10, 1.5, D is what we had, and ED. If we run that, resulting flow rate, resulting flow rate equals that. Should be returning the resulting flow rate. Let's see. We have D and ED, and we have the resulting flow rate is equal to the Newton. And it's not giving me anything. Let's see, 1, 2, 3, 4, 5. We've got 1, 2, 3, 4, 5. It should be working. We've got the QGuess up here. Do I need to do that? Oh. Okay, so this is having trouble converting, so there is something that we can do. And one thing that we are going to have to do is pay attention to the sign. So I'm going to make a new dH absolute, and we're gonna just take the absolute value of delta head, and we are going to replace delta head with dH underscore abs. So everywhere we see delta head, dH underscore abs. I think that's it. If we run this again, try running that. Okay, so it's still having trouble, so what we're gonna do is we're gonna create an if loop. So if dH abs is less than, then we want to return so that's gonna let's see what's going on here, because this should help us stay away from when the number is really, really small for dH abs. We should have, let me separate this. Oh, no, not what I wanted to do. So, okay, let's multiply by okay. We're putting in 40, 10, 45. It should be giving us the right thing. The resulting flow rate. So it's a runtime error. But that should have been fixed with this. Let's put this after. That might help. I'm not sure. Nope. 50 iterations. Okay. I'm gonna come back again, see if I can figure this out. Okay, so figured it out. What the problem was is that this value was supposed to be positive and this one was supposed to be negative. So now that that's fixed, let's test. If we put in a negative, oh, here we go. So if we put in a negative delta head, we're supposed to get a positive. So if I do that, it should fix it. So we get a positive for the negative delta head, and we should get, yep, negative for the positive delta head. So now that we have that, we're pretty good. Okay, so now that this is working, we can look at, if we look at the d head function and our f to 0 function, the insides are basically the same. And what we can do is we can get rid of this, and instead of having it give us this, we can delete that and have it give us d head using Q, L, K, D, ED, and subtract the DH absolute, and that should, oh, gotta run that one first, and that should give us the right thing. I think I don't need that. So yeah, so now we're still getting the positive D head is giving us a negative, so we're good there. And so now that we have that, we can move on to putting in this array that we saw before. And so if you give me a minute, I'm gonna split it so I can type it in faster. So I'm gonna type in this array and I'm gonna name it pipes. So np.array, and it should be in brackets. So first it should be 0, 1, 1.5, 1.5, comma, I'm gonna take it down to the other 0, 2, 2.2. Take that down again. 1, 2, 1.5, 0, 1, 3, 1.5, 0, 2, 4, 0.5, 0, and 3, 4, 3, 2. And that should be right. Actually, I think we need double brackets there. That should be good. So if we say pipes, okay, so it looks good. That's the array that we have. And we can also put in some other things. So we know the heights of the nodes, so I'm gonna name that Z, because that's what we called it here. And we're gonna have that as np.array, should be in brackets, and it should be 30, and then 0, 0, 0, 0. Yeah, that should be right. And I'm gonna put a decimal point so it's an integer. And we can also put our external pressures. I'm gonna name that external P, actually. And we can have that as an array as well. And first is 200,000, and then the other one is 0, and we should probably label our external nodes. So external nodes, and so that's going to equal an array again of 0 and 4, and so those are the numbers of our external nodes that we found before. And yeah. Okay, so basically what happened is up here I decided to import math, and so that fixed the problem. I didn't have to use NP max, so I just switched that to regular max, and I also put 2 nodes because that is the second row anyway, so I just put that. And when I run it, it works, and if I put n nodes and run it, it gives us 5, which is correct. 1, 2, 3, 4, 5. 5 different nodes, and so now we can start moving on to actually calculating some numbers. Okay, so now we can start calculating some things. So what we want to do is define a function called calcflows, and so this is going to take in heads, and what we want this to do is, well, first we want to set our initial flow to 0, and so np zeros of n pipes. So this will just help us not get an error at the end. And so what we want to do is we want to create a loop. So for I in range and we want the range to be n pipes. And basically what we want to happen is we want to take the delta head and we want to determine the flows depending on the heads. So we want to take the change in the heads between the nodes. And so we're going to take the heads, and we're going to have the 2 nodes within the range. We're going to have that minus the heads of the from nodes, also within range. And so when we have that, we also want to calculate the flows. And this is going to be using this flow that we had up here. So we will copy that. So that will equal flow, with delta head, and this L and K and D and ED need to match up here. So we're going to replace this capital L with the lowercase l, and it also has to be within the range. This one, it's also capitalized, so that pipe D also within the range, and pipe underscore ED also within the range. And we want this to return the flows. Return flows. And so if we run that, and we can test this out by making an array with random numbers. We can say, let's say 50, 40, 30, 20, 10, and have that as our heads. And we can do calc flows using the heads. And let's see. The flow. Let's see. Pipe D, pipe underscore ED. That should be fine. That's named heads, okay. Calc flows. Okay. Let's see. It's not giving me that. Let's see. So we've got flow that is set to 0 in range. And the number of pipes. Okay. Delta head is going to equal heads, 2 nodes, minus heads from nodes. Let's see, it's saying the error is in this line. Do I have a mistake in my flow? Doesn't look like it. Flows. I have that as L, this as well. Pipe D, pipe underscore ED. Let's see. Oh, you know what? I think I need to do that. There we go. So now we get this array, and that should be good. Okay, so that works. We can delete this and delete this. And next we want to calculate the net flows. So we can make another thing. So we want to calculate the net Q. And what we're going to take in is the flows. And so first we're going to set the net as 0, and we're going to use the number of nodes for that. And so what we want to do is we want to add the flow that's coming into the node and subtract the node, or the flow that's coming out of the node. So to do that, we can do np.add.at. We could do, so if we look here, we're going to have net q. We're going to have it for the 2 nodes, so that's where it's going to be positive, so we're going to have positive flows. And then we're going to do the same thing, but we're going to have the from nodes, and that is going to give us a negative flows. And so this, we want to return net q, and if we run that, yeah, that should be good. So then after this, we are going to make a function that is going to find the roots of the net flow for all of the internal. So the next thing we want to do is calculate the net flow of the internal nodes. So we're going to make another function. It'll be net q of the internal, and that is going to have internal pressure right there. And what we want it to return is the calculated net flow depending on the flows we calculated before using the heads. And to do this, the first thing we want to do, will come up here, is that we want to set the heads np.zeros. Oh, that should be an equal, not a parenthesis. So we want to set it equal to 0 for the number of nodes. And we also need to determine how many internal nodes there are. So the internal nodes is going to be, we can say there's this list, and basically it's just the number of nodes minus the external nodes. So we can set it equal to, it's going to be in a range of the number of nodes, and this is going to be minus the set of external nodes, which we already had before. So if I add a line there and I say internal nodes, it's giving me 1, 2, and 3, which is correct. So if we look back at this, 0 and 4 are external nodes, and 1, 2, and 3 are our internal nodes. So that's good. And we also want to we want to calculate the heads of the internal and the external nodes. So we can do the external nodes up here, external nodes. And so this is going to be using a formula. It's just going to be the external pressure divided by rho divided by g plus the height of the external nodes. And so that is going to be the same thing for the internal nodes, and we're actually going to put it inside of our function. And so internal nodes, oh sorry, we need heads of our internal nodes, and this is going to be equal to the internal, that's not, internal pressure divided by rho divided by g plus the height of the internal nodes. And so once we have that, we can go on and use a root function, which I'm going to load up here, and so that is going to help us get some real numbers soon. So now we need to make a guess for the heads of the internal nodes. And so what we're gonna do is we are going to make a guess. So we're gonna name that internal head guess. And this is going to be equal to, we're just gonna take the mean of the external nodes. And that we're going to take the mean of the heads of the internal nodes. And then we're also going to make a guess for the internal pressure. And so how we're going to get this is we are going to use this internal head guess, and we are going to subtract the height of the internal nodes, and then we are going to multiply by rho and g. And now we can use this internal pressure to and the root equation to give us an array for the unknown internal node pressures. So we're going to call this result. And so this is going to be equal to root of net Q internal and internal P guess. And we'll do that, and it should give us an array like that. So that's good. So now that we have these numbers, we can calculate and store our numbers in some arrays. So our calculated flows is going to be equal to calc of flows of our heads. And we're going to make a for loop. So for I in range, we're going to have n pipes. So this is going to give us the flow through each of the pipes. We are going to have it as, we're just going to print f from, and this is going to be int pipes, and this is going to be I to 0. And then we're gonna have, I'm just gonna do tab 2. This is going to be int pipes from I to 1. And tab again, and we're going to have flow, which is going to be, no, not int. It's going to be calculated flows, I, and that is going to be that. Let's see. Oh, I see. I need a parenthesis there. Gonna need one there. That should be good. Here we go. So this is the flow from 0 to 1. That's the flow. And we're gonna do the same thing. Calculated underscore net Q equals calc underscore net Q of calc underscore flows of the heads. And we're going to do the same thing for I in range. Oh, I'm sorry. We need to put some stuff first. First, we need to have pressure equal to NP zeros of n nodes. Gotta set that equal to 0. The pressure of the external nodes should be equal to the external P, and the pressure of the internal nodes should be equal to the result dot x. And then now we will have our for loop for I in range of our n nodes, and we'll have print f node I pressure with I z, which is the height. That's also going to be z with regards to I, and net q is going to be equal to the calculated net q relative to I, and that should be it. Let's see. Oh, I see. I need an underscore there. And those are our values. So we use this code and we ended up finding the flow through each pipe and the pressure, height, and net flow in all of the nodes.